Well, welcome. Thank you, everyone, for coming today. I'd also like to thank our keynote speaker, Robert Hastings, who traveled here yesterday from Switzerland, and he's looking fresh still. All of our workshop presenters who've also traveled here, and to John Lloyd, who's representing the hard work of all of our Efficiency Vermont staff who put together this conference so over 1,000 of us can enjoy, share, and learn. We like to use this conference every year to highlight the best of the best in design, build, and renovation projects from around the state. These winners have mastered linking energy efficiency with durability, beauty, and practicality. I'd like to take a moment now to recognize our 2013 winners. We have 4 broad categories we're going to look at today. The first category is commercial building design and construction. And within that, we're going to give 2 awards out for small new construction, under 15,000 square feet. Our honor award goes to the Vermont State Employees Credit Union by Gossens Bachman Architects. Our merit award goes to Jiffy Mart by Champlain Oil Company. In the large new construction, those projects over 15,000 square feet, our honor award goes to Avenue Apartments by Scott and Partners Incorporated. Our merit award goes to Community Health Centers of Burlington by Freeman French Freeman. And in the major renovation subcategory, gut rehab, our honor award goes to Bennington Superior Courthouse and State Office Building by McClay Architects. Our merit award goes to the George D. Aiken Center, University of Vermont, again by McClay Architects. The second category of awards goes for residential new construction. And our first subcategory is comprehensive efficiency. Our honor award goes to the Landau Residence by Stephen and Barbara Landau. Our merit award goes to the Comstock Residence by Reese Building and Renovation. In the subcategory of innovation in energy savings and design features, again under residential new construction, our honor award goes to the Lemon Residence by Andrea and Ted Lemon. And our merit award goes to the Kaylock Residence by Yandao Green Builders. And still in the category of residential new construction, our partner of the year goes to Pil Maharam. The third category is building performance. And our honor award here goes to the Waterville Post Office by Caleb Contracting. And our merit award goes to the Roxbury Senior Center by Energy Smart of Vermont. Our last category is home performance with Energy Star. And our first subcategory of awards is for home performance projects costing less than $8,000. Our honor award goes to the Kelly Home by Weatherization and Renovation of Montpelier. And our merit award goes to the Healed Home by Caleb Contracting. For our awards in the home performance projects costing between $8,000 to $12,000, the honor award goes to the Alexander Home by Caleb Contracting. And our merit award goes to the Youngstrom Home by Red Barn Design Build. In the last subcategory, those home performance projects costing more than $12,000, our honor award goes to the Smithers Home by Caleb Contracting. And now, please, let's all give our winners a round of applause. So before we move on, we can never have this conference without going over a few housekeeping issues. First, for all of you, as you leave your trainings today, make sure you scan your tag so that you can get your continuing education credits. Also new this year is we have QR codes, and those QR codes lead you to an easy way to fill out those evaluations. Should you not want to do the QR codes, you can still do an evaluation the traditional way on paper. All of our Best of the Best award winners, if you can see this gentleman down there, Bob Murphy. Bob's got his hands up. Bob's going to help direct you to get your photos taken right after the keynote speech. Thank you, Bob. All presentations through the 2 days here will be presented on the Efficiency Vermont website, and they'll be posted later on this week. Look for efficiencyvermont.com/conference to find these presentations. Coffee will be served downstairs in the exhibit hall after the keynote speech, and I'd highly encourage you, while you have your cup of coffee, to walk around and see our exhibitors who've put a lot of effort into setting up their booths and attending this conference. So now, this year, as you know, we're focused for the conference on international best practices. And over the next 2 days, we hope you will get to attend different sessions, several workshops exploring the best practices in efficient building across the world. With our international theme and our keynote speaker traveling from Switzerland today to share his wealth of knowledge and experience, I wanted to set the context for this year's conference in the form of a question. If this conference was being held in Europe, would the efforts of all of us in Vermont rank as international best practices? Well, I would definitely, with a little bias, surely, say absolutely yes. The efforts of many of you, and all of you in this room, I should say, have really helped put Vermont at the forefront of much, and we have a lot to be proud of. In the next 2 days of sharing and listening, it's important to remember the different approaches other parts of the world have taken to be able to achieve their goals, sometimes in contrast to how Vermont does it. In much of Europe, they've enacted very stringent building codes, along with strong regulations in achieving their goals. This approach has led to market innovation and led the market and driven innovation. There's no question that the results have been very impressive. We had dinner last night with our keynote speaker, and some of the regulations that are in Europe are very impressive in terms of actually testing your flue gas residue to see what you're burning. I don't know if in America we would actually appreciate that happening. And in Vermont and across the U.S., we go about it a different way. We don't necessarily use that heavy hand of regulation, and we rely on using the marketplace to jumpstart efficiency. Sorry, John, we can go to the next. So in Vermont, we have some great examples of the tremendous opportunities that our market-based approach can reveal. And those elements will be highlighted in the conference among the international best practices over the next 2 days. And this function, it's the function of this conference to promote and to share many of these elements as possible each year. But what I really want to highlight this year is some of the future-looking participants in conferences that we're having, or workshops. The imperative we face as a world, and we're going to address as a state, is how do we battle greenhouse gas emissions and climate change. Our natural inclination is to treat renewables, thermal efficiency, electrical efficiency, transportation as silos. And because of this, I often hear, well, our electric portfolio is so clean, we really need to go focus on transportation. We really need to go focus on thermal efficiency. Well, I think there's a fallacy in that argument. And that's because at the end of the day, we need all of those together. If we want to reduce our greenhouse gas emissions, we're going to have to think about how do we move transportation to our electric sector, or a portion of it. Same thing with our housing stock. How are we going to move some of our heating needs to the electric sector? To do that and to not increase gas emissions, we're going to need to make sure that we have plenty of headroom in our electrical infrastructure and that we're using clean energy to supply that energy. The point is, even if we do that, can move to the electric sector, we also need to make sure that our homes are as tight as possible so we're not wasting that energy. So the point here is it's not that it's one or the other. We need all of them together. So if I haven't made the case yet, clearly our goal at Better Buildings by Design is to be able to have a discussion about these things, to provide a focus for all of us to come together and think how we're going to address these problems, and hopefully become more informed and more energized to go out and help serve Vermonters better. So lastly, just to kind of highlight some of the progress we've made here as a state in addressing our climate issues and helping provide economic benefits to Vermonters, I have a 5 points to bring up to you. First off, in Vermont over the last 10 years, we've saved enough electricity to power Vermont's homes for 2 years. Very impressive fact. Electrical efficiency is also the second largest producer, if you can wrap your head around the fact that saving energy can also be viewed by the grid as producing energy. Energy efficiency is the second largest electrical producer in the state of Vermont, right after Vermont Yankee. We've improved more than 5,000 multifamily housing units. Nearly 3,500 home performance with Energy Star projects have been finished and generating more than $30 million in lifetime energy savings. Last year, for the first year, we broke 1,000 home performance with Energy Star projects in a single year. This year, we're not going to sit back. We're actually going to try to do 1,750 home performance with Energy Star projects. So tremendous growth continuing with home performance projects. We have one of the highest concentrations of BPI certified contractors in the nation. And as a state, we recently completed a roadmap for thermal efficiency through a collaborative process involving more than 50 public, private, and nonprofit stakeholders. It's a tremendous effort by that group to really come together and see how we can collaborate mutually to address our thermal efficiency issues. I think we can agree that these results are impressive and qualify our small state to be up on stage sharing the limelight of being amongst those that can say we have some of the best international efficiency practices in the world. So thank you to everyone in this room for helping make that be possible. Now I'd like to introduce our keynote speaker today. As I mentioned before, our keynote, Robert Hastings, comes from Switzerland. Robert is an international expert on efficiency design. He has written 9 books on sustainable building and has addressed Congresses in Europe, China, and North America. His impressive career includes practicing as a licensed architect, I believe in the state of Massachusetts as well, conducting building research at the U.S. Center for Building Technology, the IEA, International Energy Agency, and his own firm, Architecture, Energy, and the Environment. He teaches as a professor and was head of the Buildings and Environment Department of the Danube University Krems in Austria. Please join me in welcoming Robert today.
Thank you very much. This is awesome. I have a couple of questions before I get started, and they're not administrative, they're personal. Do you mind a personal question? Who here is from Vermont? Okay. Now, everyone closes eyes, but who's from New Hampshire? A few people, okay. And from Maine? Massachusetts? There we go. Is Rhode Island a state, or is that... Rhode Island? Connecticut? There we go, that's good. I think I got them all right. You see, I read Yankee Magazine, that's good. You know Yankee Magazine? Yankee Magazine is for people who aren't New England anymore and like the romance of New England. Oh, I forgot, is anyone here from Alabama? Not one person, okay, good. Oh, I'm sorry, I didn't say good, no. That'll cost me later, I'm sure. I'm going to talk to you today about a story. It's a time journey through solar architecture. And who's an architect here in the room? Very good. And who's a builder? And who's an engineer? And who's a lawyer? Whew, that's a relief. Good. Good. I'm going to be talking to you about architecture. I'm going to be talking to you about building. I worked for a builder for a while, Pulte Homes, and I was a snob young Ivy Ivy League college graduate, and I thought, oh God, this colonial pseudo Disneyland architecture is not for me. And what I learned working for Pulte Homes is what America is extremely good at. It takes a concept, it optimizes it economically and engineering-wise, and produces an extremely good product. So I learned a lot about carpentry, drywall, appliances, plumbing, electrical, and costs working for Pulte Homes. I also worked for an inventor and a sculptor, Buckminster Fuller. Did you ever hear of Buckminster Fuller? Yeah. I worked a year for him, and most of the time, he never came into the office because he traveled and talked all over the world all the time. And when he would talk at Harvard, they'd have to televise it because you couldn't get all the people in the hall. And then he'd come into the office, and that was a disaster. And it was a disaster because we were an architecture office, and everyone sit on the floor the entire day and listen to Buckminster Fuller talk. That's expensive, yeah. So this story is a lot about my personal experience. It goes back to 1900, and I don't go back to 1900, but I know people who did. And so it's directly relating to what I've learned from a lot of people. First about Vermont. For those of you who are from Vermont, it's really a tiny state, good heavens. But to get that in perspective, it's 2/3 the area of Switzerland, which is a country. So it's not so tiny. In fact, if you think about Europe, a lot of European countries, if you discard Germany and France, are quite small countries. Look at Luxembourg. I'm sure it's much smaller than Vermont. And so quite honestly, I am awestruck, literally awestruck, and a little terrified to be up here in front of so many people in such a small country like Vermont. That's amazing to me. And this is the second time I've talked at a big event. The first in the US in the last couple of years. I've talked also in Shanghai. That was hard. But I talked in Portland to the American Passive House Conference. And what I sense here from the little bit of contact I've had with you in the exhibition room and last night, and what I sensed in Portland is such an enthusiasm and excitement. There are things happening now. There are things going to change, and we're doing things now to prepare for that change. And that's exciting. That's really exciting. So I'm very, very, very awed by how many people are committed and innovative and doing good things to get us ready for the transition. You asked me what's a little bit different from Europe, from New England, for example. What I notice in Europe every day is they're talking about the Energiewende. That's German, and it means the energy change. This is imminent, the energy change from a fossil fuel civilization to something else, and it's exciting. In Switzerland, we talk about 2,000 watt society, and the 2,000 watt society is to say the new rule for how much energy people should be targeting to use is 2,000 watts. And that's not energy, that's power, 2,000 watts. But the way that comes about is you take all your energy that you've used for milking the cows, driving your Mercedes. Farmers are well paid in Switzerland. Running your electric lights, watching television, everything you use for electricity, for gas, for oil, whatever, divided by the number of hours in the year, and that should be less than or equal to 2,000. It's an interesting exercise. So try it. Try to summarize all of your energy, divide it by the number of hours in the year, and see how close you get to 2,000. This time journey we're going to take now starts back earlier. And did any of you like history in high school? Who liked history in high school? I thought history was terrible because you had to memorize stuff, and I was kind of stupid. And I couldn't get the dates right, or the generals, or the presidents. So I didn't like it. And now living in Europe, I think it's pretty exciting, history, and I think you can learn a lot from history. And I think we don't learn enough looking back over history. And so my mission this morning, with the privilege of talking to each of you, is to look a little bit back over history and see what trends can we identify which might help us anticipate a little bit what's coming in the next years. And talking of trends, this is a story about a guy and his wife calls him on his cell phone and says, Robert, take care. Someone is driving in the wrong direction on your Autobahn, on your highway. Well, in Switzerland, we drive at about 70 miles an hour. In Germany, you can drive 120 miles an hour. If someone is coming in the opposite direction in your side of the highway, that's a serious problem. So this guy says, honey, I just heard about that on the radio. The wife says, somebody's driving in the wrong direction. And the guy answers back to his wife, honey, there isn't just one. There are hundreds and hundreds of idiots driving in the wrong direction. And guess who's driving in the wrong direction? Robert, yeah. So it pays to know what's coming ahead and what the trends are so you can prepare. Let's start back in the period 1900 to 1925. And I had a very good book called The Golden Thread, which is now out of print, but it's about to be reissued. And it's an exciting book about the state of solar energy in 1900. And I didn't realize this, but you know who led the world in the application of solar energy for heating in the world, in the U.S., is U.S., 1900. And there were guys making solar water heaters in the U.S. in 1900. This is one called the Day and Night Solar Water Heater in Pomona, California. How can a solar water heater work at night? Sounds like a trick advertising. Who's in marketing here? This sounds like marketing to me. Uh-oh, there we go. Yeah. Well, how does it work at night? It has a storage, of course. And that's an interesting dilemma to get the storage matched to the collector, to the need. And this first storage was mounted on the roof, simply black tanks, steel tanks painted black. You put it on the roof, and it gets hot, and then you can take your bath, and you don't have to burn firewood to take your bath. And the whole idea of these solar collectors is not an American invention. It comes from French physicists in the late 1800s experimenting with even concentrating dish solar collectors, but the Americans thought, that's a good idea. I bet I can make some money out of that. And they built companies which produced workable servicing solar hot water systems. The first generation, as I say, was just a black tank sitting on the roof. Of course, it cooled off at night. So the second generation, they fixed that a little bit. They put the black tank inside of a wooden box with a glass cover, and that cut down the radiation losses and the convection losses of the collector. And then the third collector generation looks exactly like what we have today for thermal collectors. It's a flat plate collector sitting on the roof with a tank up in the attic. Do you know why they put it in the attic? Gravity make the tank fall down. That'd be bad. I wouldn't want to take my bath under that tank. It's exactly right. Gravity feed, it's the thermosiphon system. The hot air and the hot water in the collector by gravity circulates up to the tank because it's less dense. So that's a third generation collector, and we're not even up to 1925 yet. At the same time, you can transport heat from the collector with air instead of water. And transporting it with air has certain advantages. Air doesn't freeze until you get to a very, very low temperature like you have here in Vermont. That's a joke, but boy, it's cold here. Whew. And I worked 4 years in an international team looking at solar air systems. So if you'd like to learn about solar air systems, contact me. You can get a copy of the book from the publisher EarthScan. There are 2 volumes. One is on systems and engineering, and one is on buildings which use solar air systems all across Europe and Canada. This is an example of a solar air system built by Morse in Salem, Massachusetts. Again, evidence of the ingenuity of American engineers and marketing people taking a concept and making it viable. Then in the 1920s, gas was discovered off of California. The price of gas got really cheap, and it literally killed off this first generation of solar collectors. And we're going to see several cycles of solar collectors being killed off and then reinvented. So it's interesting to see that in the 20s, that was the end of the economic viability of any kind of solar collector. But what we saw after the period 25 to 45 is a new modern, I say modern in quotation marks, solar architecture. Any of you who have studied architecture, and maybe even the engineers, have heard of Frank Lloyd Wright, is that right? Yeah. He's my favorite, honestly. I was forced to study Corbusier at Cornell, and I didn't like Corbusier. I like Frank Lloyd Wright. But maybe that's because Corbusier practiced in France. That could be. There's a rivalry between France and Switzerland somewhat. A beautiful architecture, beautiful architecture. We see mass, we see play with transparency, light and darkness. And the idea of transparency in architecture really was not viable, although the Romans had glass and they used it as glazing for buildings, but it wasn't a viable solution in a mass scale until the first breakthrough in the glass industry, and we're going to see 3 breakthroughs. And this was in 1927. I'm going to guess it was a German guy, invented this idea of pulling glass, molten glass, over rollers vertically high so that you got big sheets of glass, and then you let it cool down slowly so it doesn't fracture, and you got the possibility all of a sudden to have large glass areas in architecture. Before that, if you look at colonial houses, the Salem Witch House, for example, the windows are pretty small because you didn't have much possibility to glaze them. Now you could do huge glass areas. And for me, it really lightened up architecture. So this Mies van der Rohe German pavilion in 1929, that was really beautiful, pure, simple architecture. I like this. In terms of energy, well, that's another subject, but the architecture is fantastic. And that had to be solved, this energy dilemma, by the second breakthrough in the glass technology industry, where in 1935, PPG and LOF, and when I give this talk in Europe, I say, does anybody know what PPG or LOF is? They say, huh? Nobody knows of it, but they invented the idea of taking 2 sheets of glass and then fusing the edges together to create a captured air between the 2 sheets of glass. This fused edge technology seems pretty impressive to me. It's gone. We don't see it except for the new generations of vacuum glass. Today we use a butyl spacer and some kind of a plastic spacer, and it's a different technology. But the idea is glass is such a good conductor. You have to have something which insulates, and that's the air gap, which you've trapped in between. Excuse me. So now all of a sudden you could do big sheets of glass, big transparent areas, and it doesn't lose heat like crazy. In fact, the U value of a single pane window, I have to give it to you relatively because I've forgotten the U values in the British thermal units. But a single sheet of glass has a U value, loses about 5.5 watts per 10 square feet. 5.5 watts per meter squared. This new insulating glass lost about 3. So we went from 5.5 to 3. We almost halved the heat loss. That improved comfort, and it, of course, improved your heating bill. And now we get guys like the Keck brothers in Chicago building large glass areas to the south, and they learned, I don't know where they learned this, they didn't learn it in college because we didn't teach that kind of stuff back then. They learned that you got to have mass and you got to have a solar overhang to protect you from the sun in the summer. So they did really good architecture and made headlines in the Chicago papers in the 40s. This house needed no heat at minus 10 degrees the entire day. And in the night probably was cold, but you had all that warm mass from the day's sun storage. A more engineering approach is, of course, to put the storage not on the floor and in the chimney and in the walls, but you put it in a big, big, big tank underground under the house. And this is the first of a series of experimental houses made by MIT in 1939, and it was a semi-seasonal storage solar thermal system with a whole south roof slope collectors and a monster underground tank. And this concept we still see experimented with by pioneers in Austria, in Germany, and in Switzerland, a huge tank. In fact, there's a guy, Jenny, if you look up Jenny on the website, Joseph Jenny in Switzerland, he markets as a commercial product, as a company, monster tanks for multifamily housing. And he built a 12 apartment, 4-story building with no auxiliary heating system, just a monster tank in the middle of the house and a lot of solar thermal collector area. Second World War came along, and there were no resources to do any more research or product development in solar energy except in the area of solar air systems, because George Lerf had a private sponsor that kept him busy further developing this idea of solar air systems. And in fact, to prove the concept, he got his wife to agree that they should make their house as a guinea pig. And you can see they put a solar air system over the entire roof of the house. And in Boulder, Colorado, you have two things. You have really cold weather and really a lot of sun, even more than Vermont. Not a lot of sun here, right? But Boulder, Colorado, you should have a part of their sun. And the house performed perfectly by -0 temperatures during the daytime. But this whole idea of solar air systems almost cost George his marriage, because at night the house cooled off immediately. It was a 2x4 house, and the wife froze, and she said, "George, enough of this experimenting stuff. I want a wood stove in here." And so George was confronted with a problem, and he said, "Well, honey, give me a couple days to think about the choice." Reminds me of Jack Benny. You remember Jack Benny? And he's going to the subway and wherever in California somewhere, and he gets held up by bandits, and they say, "Mister, your money or your life?" And then there's a long pause, and the bandits say, "Come on, we haven't got all day. Your money or your life?" And Jack is saying, "Just a minute, I'm thinking about which I prefer. I don't want to give it up." Well, George finally decided what he needed was a compromise, and he put a rock bed storage in, and the rock bed storage took care of the day-night problem very effectively, and so George stayed married the rest of his life. That's a happy end. And the system proved viable, and he marketed that as a solar air system. If anyone is interested in solar air systems, I'll show you examples later. There's a very good product in Germany called the Grammer solar collector. I don't get paid for this, but it's an excellent, very highly optimized, engineered solar air system. And then there's a very good system in Canada, invented by a Swiss guy and then developed and marketed in Canada, called Solar Wall. And these are extremely interesting systems for warehouses, industry buildings, where you have large volumes of air and large roof areas. The 45 to 70 years after the war, we see a simplification of solar architecture. This is a very beautiful house, Mies van der Plano house in Farnsworth, Illinois. Not an energy-saving house, but again an example of working with glass and beautifully creating fully daylit spaces. More energy conscious were some of the prototype houses developed by star architects. I mean, really the heroes of young architecture students in college, guys like Luke Kahn. And this is a prototype solar house stolen from the ancient Greek Megaron house before Christ. So we have a concept being developed now thanks to insulating glass from PPG and LOF with a lot of mass, and you can see it's a little bit in plan, funnel shape, to give you a larger south-facing glass area. What's exciting is the whole idea of solar architecture is no longer an exotic idea. We start to see solar architecture in everyday magazines like Look and Life, marketed by companies. Your solar home is all wrapped up. And that's exciting to see now. It's among the people, the idea of building architecture to work with the sun. 1960s, energy got cheap. I mean, really cheap. I was in college in the mid-60s, and I had a Volkswagen, and I paid 25 cents a gallon for gasoline. 25 cents a gallon, unthinkable. It almost doesn't pay to collect the money to fill it up. You just might as well let them drive away. It's so cheap. This is the Richard Meier house, and it's exemplary of really cheap energy because you've got an awful lot of glass area there, much more than you can use. In passive solar architecture, you have to always balance what you're getting in by what you lost against what you can store. This house didn't balance that. It's got a terrible overheating problem. Doesn't matter. Oil is cheap. Oil is really cheap. And so you can do any architecture you want. And if you do something stupid with too much glass and it overheats, you can solve it. Because you just put in a lot of air conditioning and a lot of heating, and it takes care of it. Now architecture, as opposed to architecture as I perceive it in Vermont and in New England, it's not climate adaptive, it's climate combative. So climate is your enemy. You build a barrier, and then you solve the discrepancy of whatever the gains and the losses are with mechanical engineering. Excuse me. Good time for mechanical engineers back then. And the mechanical engineers could fix any problem which an architect created. They just put in a bigger system, and the bigger system could handle it. I wonder what that thing is there. It looks like a turbine from GE or something. The trouble with this, I'd like to point out by a little story. If you have too much blind faith in solving problems with technological fixes, this could happen. Here's a door-to-door salesman. Did anybody sell stuff door-to-door as a Girl Scout or a Boy Scout? Cookies or something? Yeah. Were you successful? Did you sell many? Lots of cookies. That's good. Christmas cards or turkeys or I don't know what. Magazines, yeah. What did you sell? Encyclopedias. There we go. That's hard to do today, I guess. Yeah. Anyway, this guy, this is marketing, so this is for you. The trick is you go door to door, and the first reaction you get is the door closes in your face, right? Because like telephone marketing today. Well, the answer is you stick your foot in the door so they can't close the door. A good technique. And then this guy who was clever, he would had a little plastic, in those days, a paper bag in his pocket, and he threw some chicken manure or cow manure or some kind of manure into the front entry hall. Well, that caught the attention of the houseman or housewife for sure. She was upset. She said, "What are you doing throwing manure in my front hall?" He said, "Madam or sir, I bet that my vacuum can trace up can suck up every trace of manure in your front hall. And if you find one trace left, I'll eat whatever's left." And the houseman or housewife got a huge smile. And he said, "Oh boy, you know, our electricity we had a power failure since 8 o'clock this morning." So you can imagine, boy, would I love that. And that's why I don't do door-to-door marketing now. Yeah. So you can't be too confident, and that's going to happen more and more when we talk about smart grids, the electric grid problem. A big problem and discussion in Europe because the wind energy is in the north, and the demand is more in the central and south part of Germany, across Switzerland, Austria. How do you get electricity from the wind generators up on the North Sea down to where the people need it? And the transmission lines aren't there, they're private. So you got to encourage investment to get the wind generated power down south. In the day, there's a lot of photovoltaic power in the south of Germany, but you need that wind power at night when there's no photovoltaic power. That's not so interesting as an investment if you can't run the power lines full gas all day long. So it's a dilemma, the whole idea of electricity. It's a big dilemma in Austria also, where they're interested, and in Switzerland. The big demand at the moment is how can we increase the electric delivery from Germany and France at night into Switzerland when they don't know what to do with all that power. You can imagine the power the French are producing with nuclear reactors. You can't just shut a reactor down and go home for supper. The thing runs all night. Nobody needs the power. And the Swiss and the Austrians say, we'll take it from you. Sometimes the French have to pay the Swiss to take the power at night. Can you imagine you have to pay to get rid of your power? And that's why I heard sometimes you shut down wind generators here because there isn't a source of demand because your wire isn't thick enough going down to Manhattan. If you got a bigger wire down to Manhattan, you could probably sell it all the time. But that's a problem. And so the answer which the Swiss offer in competition with the Norwegians is we'll buy your power all night long, cheap, and we'll pump water up into our reservoirs in the Alps, and then in the daytime, we'll generate electricity and sell it to you at 4 times the price. And that's why Switzerland is not a poor country, this kind of thinking. And I understand you have a lot of hydropower in Vermont. In fact, in New England, the hydropower is pretty good because you can shut down a turbine pretty fast. So it makes sense to use your power when it's available from other sources and then save the water in the reservoirs. 1972, all of a sudden the good times ended, and abruptly they ended. Who was here working for a living and driving a car in 1972? Remember the inconvenience of not being able to get gas? Boy, in Virginia, I don't know if this was nationwide, but you had a license plate. You could only get gas on even days when your license plate had an even number. You waited in line a long time, and it could happen after you waited in line that the gas station sold out. And then you're really upset. So this was hard times in a civilization which took energy for granted. As I showed you earlier, energy was just no topic in the 60s. And this is what's exciting about being back in the United States of America. If you back Americans up against the wall and you say, you're in deep trouble, guys, they don't say, oh, heck. They don't give up. They say, all right, let's fix this. Let's roll up our sleeves and let's fix it. And you don't realize it because you probably, a few of you have ever lived extended periods outside of the U.S. But this is a really special Geist, that's a German word, ghost, or so character, spirit of American innovation. Let's fix it. And this let's fix it attitude in 1970s is exactly when I began being an architectural researcher at the Center for Building Technology at the National Institute of Standards and Technology. And what a great time it was to be an architect and to be involved in energy research. And we see really great people doing things like Ed Mazaria, the passive solar book, William Shercliffe, thermal shades and shutters. We see a lot of innovative solutions to storage, to window apertures. Great time. The U.S. Department of Housing and Urban Development had a grant program. I was privileged to be one of the evaluators for the grant program. We went to Denver, Colorado for 2 weeks. Experts from all over the United States in about 1976 and evaluated by computer simulation and expertise hundreds and hundreds of really clever inventions to solve the problem of how can we really reduce by a 10 factor the energy needed in buildings, be it commercial buildings, be it institutional buildings, or be it residences. It was exciting. There was a good guy in the White House then also, and we see the creation overnight, and again, this is let's fix it, guys, of ERDA, the Energy Research and Development Administration. We see the bomb guys in Los Alamos who invented and developed and made the first atomic bombs worrying about being unemployed, and all of a sudden here's a chance to do physics, solar physics. And they really advanced for the first time since the 1890s in France, the whole technology of how can I capture, convert, and store solar energy. nuclear physicists in Los Alamos. And one thing they did is, let's look how it's been used historically. There were a couple of French architects, again French, and they built a so-called Trom Wall. Jacques Michel and Félix Trom, two guys, in the Pyrenees section of France with a lot of sun. Well, the Los Alamos guy said, this looks pretty good. You know what a Trom Wall is? Well, let me tell you quickly. You just take a concrete wall about, let's say, 12 inches thick, reinforced, and you paint it black, and the sun's going to warm that baby. That's going to get hot. But at night, of course, it's going to radiate and convect the heat away. Not good. So you put a glass facade about 6 inches offset from the wall, and now the radiation and convection losses of the concrete wall are drastically reduced. And now the heat, which is stored in that concrete from the 8 or 10 hours or 4 hours or 6 hours of sunshine, slowly migrates inwards and heats the inside of the house at night when there's no sun. So you get direct gain in the daytime and indirect gain through radiation at night. Good system. Well, the Los Alamos guys took a house, Bruce Hunn's house, and they built this thing. They put sensors about every 10 inches over the entire surface area, monitored it for a year, built a computer model, experimented with a computer model. You have to remember in the 70s, computers weren't powerful like they are today. I was told that on a Hallmark birthday card, which sings happy birthday to you, there's more computing power than was present on the first moon landing computer. So in those days, computer modeling was pretty tough. You had IBM cards. Remember IBM cards? Nobody remembers that, but there were IBM cards, yeah. Didn't have keyboards. There was also a problem. We said large glass area, we said insulating glass, you cut the heat loss by about half, but it's still not enough. And if you want to have a lot of passive solar gain, you got to have a lot of window area. You just got to. And that window area loses heat like crazy at night, because if you think about it at night, if you're on a clear sky situation with a lot of stars up there, the stars suck the energy out of the window all night long. That's due to black hole gravity forces. You can say Hastings taught you something today. Yeah. But in fact, the sky radiation is typically up to 10 Kelvin colder than the ambient temperature. You got a big heat loss problem at night, especially if you've got a skylight. And so, again, American resourcefulness. Guys thought up all kinds of products and started marketing cut window losses. A quilt, which you fold down, skylights, which were gravity tilted shut at night with a small Freon canister. And here's our vacuum guy on the right. This is the guy who finally decided he'd eaten enough manure, and he changed professions, and he became an engineer. This is my architect rivalry with engineers here coming up. And he developed what's called the bead wall. He took his Hoover vacuum, which he couldn't sell, and he hooked it up to a tank of small polystyrofoam pellets. And he pumped these pellets into the polystyrofoam gap in the glass. He's got insulating glass with about a 4-inch gap. And he fills that up with pellets at night, and now he's got a pretty good insulation panel. And then in the daytime, he cranks up the vacuum, the Hoover, and pumps all the pellets out, and he's got a clear window. Sort of clear, yeah. The sort of clear problem was the pellets, when they rubbed against each other all the time, produced dust. So you had a dusty window. But, that he solved with an anti-static spray and stuff, which was being developed for computer disks. And then I thought, well, computer modeling is a good thing, but if you really want to sell components, and I liked manufacturers of components, be it wall systems or window systems, the most convincing argument is measured data from a national testing lab. And so I built a test house in 1978 in Gaithersburg, Maryland, and it had 4 test rooms in the front and 4 in the back with clerestory windows. And you could very quickly substitute the facade to change different panel systems in to get measured certified data from a national testing laboratory to help sell your component. So that was a lot of fun. Then in 1979, This was not a good year. I probably offended people. I was warned not to offend people, but this is no fun if you don't offend. You have to offend somebody or it's no fun, right? So and I was here, but I didn't vote for this guy. We voted for a cowboy, not even a good cowboy. He was a second grade B cowboy. And this entire enthusiasm in America about solar and energy efficiency, and let's build it right and let's think of the future, nope. Overnight, this cowboy eliminated the solar program. Overnight, this guy eliminated Robert Hastings' job. Yeah. Well, that's enough to make you sour, right? And I was sour, yeah. The entire program at the National Institute of Standards and Technology cut 2,000 people on the street overnight. And they said, well, you can bump. You know this word bump? You could bump the janitor and work as a janitor here if you'd like, Robert. But at the same time, I got an offer from Switzerland and Sweden, and they said, we think renewable energy is extremely important, and we're very impressed what the Americans have done in the last 10 years, and we'd like to steal your know-how. And so I had a choice, stay in a country and work as a janitor at the National Laboratory, or go start a solar program in Switzerland. Guess what I chose? Yeah. So I went to Switzerland in 1980, and I am patriotic. I'm a Vietnam-era veteran, but I thought I could do more advancing renewable energy where people want to do it and they're going to fund it. So I went to Switzerland, and in fact, in this period, it was a good choice because Europe was extremely excited by what America had done in the last 10 years across Europe, Germany, Austria, Switzerland, Scandinavia. If you were an American there, they wanted to pick your brain because they thought, you guys have done some good stuff. This is an example of, it's a question of taste, but I think pretty nice architecture with a lot of glass, sun spaces by an architect, Felix Kunig, playing with the idea of solar architecture. This is a house built by a translator. Flo Stubbe translates simultaneously in 10 different languages. That's awesome to me. You ever think about how they simultaneously translate? They're listening in one earphone and speaking in another language at the same time. You ever seen that? It's awesome. It's awesome. I've tried to do it a little bit, but I start stuttering. It's hard. And here this woman thought, I want to do a solar house, and she designed it with her architect together. And it's a direct gain house with a lot of glass area, a massive floor, and needs almost no heating near Lake Geneva. Now we see the Jacques Michel and Felix Trom Wall, which was invented and built in the Pyrenees in France, got optimized by physicists in Los Alamos and brought back to Europe, for example, by the Swiss. And this is a direct overtaking of the Trom Wall concept, optimized from Los Alamos in Lausanne, near Geneva. And this house was an embarrassment. It was a disaster. It worked miserably. Wow. And that was a problem. Do you know why it worked so badly in Lausanne compared to Los Alamos? What would you guess? No sun, yeah, that's a problem. You got a lot of wall concrete. Concrete isn't the best insulator, and you got a little glass in front of it, and it worked great through November. Come December, January, there's just not enough sun, because remember, you guys here in Burlington, Vermont are down in the south compared to Zurich. I don't know if you realize that, but I think we figured 44 latitude, is that right? And we're talking 47, 48 latitude. So I've come down south here to Vermont to freeze. Yeah. It was a failure, and it stayed a failure for a while. Solar air worked, however. And here we have an interesting example. There's still some mobility in Europe. Here's a Norwegian guy, moved to Austria and built solar houses heated by solar air systems, very nicely integrated into this Norwegian Nordic architecture. I really like what he's built. The Trom Wall got solved by good German engineering. And if you think about it, the Germans are pretty good engineers. And they solved this problem. They said the problem is not the heat gain. We get a lot of solar on the wall, or not enough solar on the wall, but we got too much loss. So let's solve the loss problem by putting a transparent insulation between the glass and the wall. And you can do this with glass capillaries or plastic capillaries. Now when you cut the losses way down, the amount of solar radiation you need to compensate for the losses and make a net gain is viable in the middle of Europe. So the transparent wall insulation system was proven to work, and a couple of companies tried to make a product on the market, never made it. And the problem was the system worked so well that come May, June, July, August, September, October, it was too hot. It was a big comfort problem. So you had to shade the system during the summer months. And then it worked fine. But now you got a problem. You got to build a concrete poured wall or a massive wall. You got to have a glass facade in front of it, and you got to have a movable shading system. And that, against the cost and the benefit of the system, just was uneconomical. So this system, you can still find examples, you can still find somewhere to build it, but it's not actively marketed because the payback does not work. And it's interesting to learn from Europe so you don't reinvent stuff and try to apply it, which has been proven not to be cost effective. So you got to concentrate on what works. And this was the era 1990s. We're coming into the last epoch now, where we concentrate on what works, optimize it, and make architecture out of it. Here's a second generation solar house. Honestly, no better than the Keck Brothers house in Chicago, except we have better glass. Because remember, now we've gone, I forgot to say, but we went through a third generation of glass with a better insulation value thanks to pumping in argon instead of air between the gap. And this guy's built a house at 1,000 meters elevation, which is 3,250 feet above sea level, has no heating system, no heating system. And I'm always suspicious when I hear that because you go there and there's a wood stove. Huh. Well, a farmer could heat a whole house in the 18th century with a wood stove. So don't give me that stuff. But this guy had no wood stove. And the way he got away with it is he built this house as a young architect for his parents. And the parents are tolerant of their kid, right? So, but he said, no tricks, it really works. So at that time I was program director for solar research in buildings in Switzerland, and I had money, and I said, let's measure it for 2 years. So we monitored it very carefully for 2 years, and in fact, the temperature fell below 67 degrees about 30 hours a year, which is pretty darn good, with no heating system. The only heating system, if it got too cold, he made English muffins in his toaster, and that was enough. Solar air system, again, we're seeing really nice, to my taste, adaptation of Norwegian architecture, solar air systems, and now combining it with sun spaces. This is a house which would pretty well fit into Vermont, I would say. It's a nice wood frame construction house. And we see now, again, the rebirth of solar collectors. Remember, we saw the first ones in the 1900 and 1920. The second generation came with the MIT solar houses up through the 40s until the war, and then nothing. And now the third generation coming in the 90s. A whole lot of solar active systems in the U.S. after the oil crisis in '72. A lot of stuff going on then, but it died out. And it's slowly coming back, the idea of solar water heating in the USA, and I'm surprised it's coming so slowly because it's a really simple technology. It applies the KISS principle. You know the KISS principle. That's to say you find yourself a pretty young man or boy or girl or whatever, and you kiss him. Keep it simple, stupid. I learned that in the Army. And the simplest thing you can do is heat up black copper, run soldered water through soldered copper tubes, and take the hot water somewhere where you can use it. And it's a very big, you know which country has the most solar water systems per capita in Europe? That's a good guess, actually. That's a good guess, yeah. The Turkeys use gravity flow systems, but that's a good guess. Could be. We don't consider Turkey in Europe yet. But they're trying, and that goes and comes. But in any case, Austria. And that was because the Austrians, again, looked to the USA. USA can be really proud about innovation. And remember in the 70s, there were do-it-yourself programs. So a bunch of neighbors got together. In New England, when your barn burned down, what happened? Or in Pennsylvania, I know this because I grew up in Pennsylvania. Your barn burned down. All the neighbors got together and you had a barn raising. And the same thing happened with collectors. A bunch of neighbors got together. They got a smart guy who knew how to do it, and they built solar collectors. You took copper tubing, you took a roller, and you rolled the bends into it nicely with sand in it, and then you soldered it to the copper sheet metal. You put a frame around it, put a glass on it, you had a collector. That's how easy it was. You put it up on the roof and you got a system. The Austrians said, that's pretty neat, and we can do stuff ourselves too. And so that do-it-yourself American philosophy spread like wildfire across Austria. The Swiss have a lot of collectors too, but the Swiss approach is pay somebody to do it for you because you don't want to get up on the roof. And I kind of like that too, because my roof is 3 stories high. We also see industrial applications of solar water systems, and that's still a coming topic. Of course, if you make a very high efficiency solar collector, you can go above the boiling temperature and have a pressurized system and serve a lot of industrial processes up to about 200 Celsius with solar water systems operating under pressure. If you're interested in this whole topic of solar water, or in any case, solar architecture, I recommend you look at the International Energy Agency website. I worked as a program manager for the International Energy Agency about 20 years. It's shc.iea.org. Who's a PhD here in the room? Nobody wants to admit to it? Well, when you have a PhD, I don't have one, but the people I know everything. And this guy, he's a German guy, Wolfgang Feist, and he studied under a guy which I had planned to go work for. Remember I said I could go to Switzerland or Sweden, and Switzerland said, we'll start your salary tomorrow. Bird in the hand, you know that story, so that's where but this guy did his PhD, and he came up with the idea, let's think about this. I'm a physicist, and he kind of thought like an economist. He said, let's calculate how much should we reduce our losses so that I can meet the losses and maintain 67 degrees with a maximum amount of heating power of 10 watts per square meter. That's 1 watt per square foot. And the reason he did that, why the 10 watts per square foot, or 1 watt per square, 1 watt per square foot? The answer is, he thought it's interesting if you can deliver the heat. This is kind of funny talking to Americans here now, but let's try delivering the heat with air. Can you imagine that? What a revolutionary idea, deliver heat with air. And if you deliver heat with air in Europe, your maximum delivery supply temperature has got to lie about, in Celsius, 50 degrees Celsius. Can somebody tell me what that is in Fahrenheit? About 80 only? Oh, 80 or 90 degrees. And the reason for that is if you go above that temperature, dust in the air starts to smell. It starts to burn. And they thought nobody in Europe would want to buy a heating system with smelly air. So if you keep the temperature below the 80 or 90 degrees Fahrenheit, or 50 degrees Celsius, you're okay. And that's where he got the 10 watts per square meter maximum heating power. And to do that, you got to make the thing airtight. And this whole idea of passive house technology is exciting to observe growing in the United States of America across the entire country. Has anyone been to a passive house conference in America here? It's pretty good, isn't it? I mean, I find this kind of pioneering spirit really strong at these conferences. And it spread like great wildfire across Europe. In Germany, a lot of passive houses built, from row houses to social housing, apartment buildings in Kassel, Freiburg, and Breisgau, Neuenburg, Kronenberg. Really a proven concept, very quickly caught up in the media. Switzerland built a few of them, and then they discontinued the whole idea of passive house because they didn't like the idea of using a German concept. It's kind of like, would you want to use a New Hampshire concept in Vermont? No. So they renamed it Minergie P, and they took the same concept and plagiarized it. I didn't say that. And the Minergie P, and now there's a Minergie A, which is a plus energy house. But there were a few houses built, and the concept was greatly respected, and the innovation of Wolfgang Feist. The Austrians loved it, and there are more Austrian passive houses than German passive houses today. And in fact, Austria stole Wolfgang Feist from Darmstadt and took him to Innsbruck and made him a professor in Innsbruck. So if you like to go to the Passive House Institute, you can still go in Darmstadt, but the Papst is in Innsbruck. And the Sweden also built a passive housing tract development of row houses, and that's impressive when you think in Sweden there's practically no sun in December. I'd like to start to close now with some thoughts. The whole objective here was to see what's happened to the past so we can get a better feeling for the context of stuff and what's going to happen in the future. And I have some predictions to offer to you here. First of all, nothing changes unless you force it, because human beings by nature just don't like change. They don't want to change anything. Me neither. I like to get up every morning at 7 o'clock, read the newspaper, have my coffee. I don't want to change my lifestyle. I don't want to change anything. But climate change is a driving force. And we see suffering. This Hurricane Sandy was a very positive hurricane in the fact that it made us realize this is real, guys. It's coming. Second driver is expensive energy. It's getting more and more difficult to get energy, fuel, be it gas, natural gas, or oil. Look at the effort we go to get oil out of deep sea rigs now, and that's expensive. And when we have accidents, that's very expensive. Look what happened to BP with their carelessness. That makes it very expensive to get energy. The third driving force is that the population distribution of age is getting older in many, many countries. I believe also in the United States. There are more and more higher percentages of people in the elderly group than in the young people group. And that means if you're in a business as a builder or as an architect or as a planner, we need to start to rethink how we build Vermont or Maine or Rhode Island or Alabama. We've got to rethink that because we need now more single people housing. People are also marrying later. There are also more single elderly people. So we need more single housing, and the ability to pay for the housing is very limited because people are living off of pensions, or if they're very young and they're single, they may have a limited income. So that's a driver number 3. And well, how do we react to these drivers? Well, we need to build smaller living units. We need more common space so that people can meet and interact. We need denser, diversified neighborhoods, and we need community transportation solutions. And that's interesting what's happening right here in this town in all of these aspects. Burlington is, I think, quite a model city for what it's trying to achieve. We also have seen when technologies allow us to build better, these breakthroughs appear in the architecture. And there will be a next generation of windows. The third generation, after going to insulating glass, after going to argon-filled glass, actually fourth generation, is then to make selective coatings on the glass so that the glass now has a very, very good U value. Remember I said a single sheet of glass loses about 5.5 watts per square meter. Double glass with air, about 3 watts per square meter. Triple glass with air, about 2.25 watts per square meter. Standard builder glass now in Europe, probably in the US, with a selective coating and an argon filling, loses about 1.1 watts per square meter. And passive house windows, with their glazing, they're looking at something like 0.5 to 0.6. So we've gone between 0.5 and 0.6 down from 5.5 watts. So we've reduced the heat loss by a factor of 10 through the glass. The weak part of the window today, honestly, by super glazings, is the wooden frame. And this is an example of a wooden frame which got an energy prize in Austria. You can see the routed slots in there to break the thermal path so that the wood doesn't conduct as much heat out. We also see some innovative solutions to how do you get more insulation value out of the same thickness of wall. And my colleague and I wrote a book, How Do You Do a Passive House Wall? And we said, here's the rule. You got to have a U value of such and such, was 0.15, and you can do it as thick as you want, but who is the thinnest wall gets the prize. And we looked at about 10 different wall systems, also considering the gray energy, the ecological impact of the materials used. I'm sorry, it's published in German. And a technology which is stuttering along is the idea of vacuum insulation panels. It's a very promising technology because now you can reproduce the insulation value of a very, very thick wall with a very, very thin panel. Breakthroughs also in the whole mechanical systems area. What I see coming very strongly in Europe, if you have to replace your heating system, your first choice today, you get rid of your oil system because honestly, if your neighbors knew you're burning oil, you're kind of stigmatized. That's a really bad thing. So you got to get rid of that as soon as you can. You sure got to get rid of it before you sell a house. So if you're burning oil, the first choice is gas. And gas is a pretty good fossil fuel. I guess you can't beat it in terms of CO2 output per heat production, but you're still producing CO2. And you're still getting your gas at the moment from Netherlands and Norway, but also from Siberia and Russia. And it comes by pipe, and you have to consider the pipe losses, environmental impact also. So it's really only a fix until you solve the problem. By the way, the gas burners in Europe, in Switzerland by law, have to be condensing gas burners. Is that true in New England? No. Well, pretty efficient. We're talking about efficiency if you add in the heat value of condensing the water vapor of over 100% of the heat value of the gas. So it's a good system, but it's not the answer. So the answer is heat pumps. And heat pumps are a technology which made a boom in the 1980s, and they didn't meet what they promised to meet in terms of how much electricity in, how much heat out. The efficiency was something in the order coefficient of performance of about 2. That's pretty poor. You might as well electric resistance heat at that rate. The new generation of heat pumps do very well down to much colder temperatures. And the ideal kind of heat pump system, and you see it a little bit, is where you can connect it to the ground as a heat source. I was thinking here I'd connect it to Lake Champlain as a heat source because there, if you go down, I don't know, 2 meters deep, you must have a constant water temperature of 40 something. That's a pretty good heat source. So ground-coupled or water-coupled heat pumps are very, very effective. And the most promising technology, and this is music of the future, is combining a heat pump and a solar thermal system or a heat pump and a solar photovoltaic system. You think about it, a photovoltaic system has an efficiency of what? What's the efficiency of a PV system? Say what? Okay, so I got 10. Give me 20. I'm going to give you 20, 20, 20. No, you're not going to get, you get 20 in the lab, but you put it on the roof and you don't get 20. And you calculate in the inverter, you bring it down a little more. But honestly, you can probably get 12 to 15 now, including the inverter and good systems. Where'd the 85% or the 88% go? Heat. And where'd the heat go? Back way. So the idea is you take a heat pump and you take that low-grade heat and use it as a good heat source for the heat pump. Think up a clever storage system. The earth can be a storage system. That's almost free. And now you've got to combine earth storage or water storage, PV, and heat pump system. That's pretty promising. Focus shift. The big move in the U.S. now, we don't see a big move to solar thermal systems. We see a big move to PV systems to achieve a net zero energy buildings. And I'm going to talk to you more about this in the workshop on trends. And I'm not going to tell you too much now, so you come to the workshop, because I want to talk to you again. But there are some fallacies to be aware of when you go to net zero. Namely, you're not going to zero energy houses, you're going to net zero. So we'll talk about that in the trend session. So my conclusion is that we see a natural cycle driven by some kinds of forces, in this case, either technology developments, mostly in the area of glass, or the World War I and II taking away all resources, or we see economics driving innovation in architecture. And the innovation is most impressive in solar systems, but also in window systems for the whole concept of passive solar architecture, and then combining the idea of passive solar architecture and highly insulated, airtight, thermal bridge-free architecture in the passive house concept. And it's an exciting period right now. So that's the end of my time journey from 1900 until the year 2050. We have some time. We could take questions if we're allowed. And I would also like to add, I'm staying until Friday, and I would love to talk to you. So come up and talk to me. I might not have a jacket, I might have a sweater, but come up and let's talk. I'm here, and I'd like to learn from you, because there's a real, if you look at the exhibition here, it's awesome what's going on here. It really is awesome. So I'll pay you college tuition. You can teach me something. Very good. Please. 1 second, can we get a microphone? So, because that woman in the back in the white turtleneck wants to hear the question, right? Isn't that right? Yeah. What's your name in the back? Right here.
Robert, I heard you mention something in the very beginning of the talk that's related to something that I studied. I just did a thesis, and it started from looking at small homes and feeling that they were underrepresented and in a lot of systems not really being promoted. And you can think of all the economic reasons that would happen. But you mentioned in the beginning of your talk that you were looking at 2,000 watts per person.
That's the Swiss goal, 2,000 watt society,
yes,
correct.
Per capita.
Yep.
And most of the metrics I see being used to measure both energy efficiency and using energy efficiency as a standard, sustainability, don't go to the energy per person or the footprint. They look at things like BTUs per square foot. And as you know, when the house gets smaller, the same house built exactly the same way, as you get smaller, the shell area increases, and so the BTUs per square foot of floor area increases even if you build the house exactly the same way when you go from 4,000 square feet to 1,000 square feet. And so the house scores lower, despite the fact that it uses substantially less energy. So I'm just curious about how they deal with this in a place where you have a goal of an energy footprint, 2,000 watts per person, and you're using metrics to measure a building which is in watts per square foot of living area. So how do you go from looking at rating a building for its energy use to translating that to lowering the energy use of the occupants?
Okay, good question. The answer is, First of all, it differs by different country. The passive house concept talks about 15 kilowatt hours for heating and so forth, and hot water and mechanical systems per square meter of carpet livable area of the house, not counting the outside walls. The Swiss and the Austrians count the livable area, the outside skin of the envelope. So it's a problem. It is a problem, and it isn't solved yet. But the issue is, how much does a person use? And that solves it. And otherwise you get into the discussion, if you have a big house, you're using more energy per person. But you can't penalize people for having big houses, because that means they were successful. And you don't like to penalize successful people. So that's a dilemma also. Yeah, that's a dilemma. And another issue is, how much CO2 do you produce? And as opposed to the Swiss attitude, let's get the watts, 2,000 watts per year as a goal. The English have as a goal CO2 production per year. That's interesting too. In Europe, when we have the policy workshop, I'll talk to you a little bit about what the goals are of the European Union and what units they use to measure the success of their goal meeting. And there they're looking at the combination of transportation, buildings, and industry.
So Robert, I'm going to interject. I'm over here. So we have about a couple minutes left, so
Okay.
maybe we have time for one more question.
Okay.
Okay, over there. And then we'll adjourn.
You focused primarily on solar in your presentation. It was really interesting. I wasn't aware that the solar technology had been around for 100 years, and that was very interesting. I'm wondering where biomass fits into your thinking and into policy in Europe.
When we talk about biomass, I'll confess to being allergic to the term biomass, because biomass suggests anything which is biological, and that could be sewage sludge, dredge, would be biomass, but we don't burn that at the moment. So biomass really means wood, and wood can be burned in the form of sticks, firewood sticks, logs, can be burned in the form of pellets, and can be burned in the form of shavings, chips, yeah. And the chips industry was really booming in Austria, Switzerland, Germany, lower Germany. In the 90s, it's pretty well gone now. The pellet industry is a big industry because it's automatable. You don't have to go, the amount of ash over the year in a good house is negligible. It's amazing. So pellets is a good system. It makes less sense in a town or a city because of the emissions. And we see that, in fact, burning wood can be forbidden on certain days if there's an emission problem. But if you're outside of a city in a rural area, the pellets are a very good solution as a marginal area of how do you produce heat, because if everyone started doing it, there wouldn't be enough waste wood. And the pellets are attractive because they're using waste wood products. So it's a very good technology, very much marketed in Switzerland and Austria.
Okay, great. Thank you, Robert. And Robert will be around. You can talk to him
I
throughout the
applaud you.
conference, and enjoy your day.